Okay, let's go ahead and do another example of Euler's method. On this one, let's go ahead and start off with one that we can actually verify our answer, okay? So let's say we're given dy dx is equal to x plus 2 and y of 0 is equal to 3, okay? So that actually implies that the point 0, 3 is our initial condition, okay? Now remember, I need two more things. I need the approximation that I need to wind up with, right? And of course, I need the step. I need how far do I need to step over in each iteration in order to get that approximation. Now let's say that I want to approximate y of 1 is equal to 0. Now sometimes they'll actually tell you the step. They say, approximate y is equal to 1 using a step of 0.1, 0.2, 0.5, whatever. Or sometimes they'll just say with 2 equal steps or with 4 equal steps. And of course, if you're going from 0 to 1 and you're told 2 equal steps, that is indirect way of telling you that your delta x is 0.5. Now, 0.5 is a rather large step. So our approximation, if we were to take, several iterations, would be a pretty bad approximation. But we're only going 2 steps away. It'll be decent, and we'll be able to check our answer, okay? Now let's go ahead and remind ourselves what this is going to look like. Obviously, if the differential equation is wholly dependent upon x, and it's of the first degree, then I'm going to have basically a quadratic, okay? If I were to anti-differentiate this, it would be 1/2, right? If I were to anti-differentiate this, this comes from 1/2 x squared plus 2x plus c, okay? And so it shouldn't surprise us that it looks something like this, okay? I've gone from -5 to 3 on the x scale and -4 to 4 on the y scale. And we see just a family of curves. That's an upward-facing parabola with a leading coefficient of 1/2. I mean, it looks very standard, kind of like it should. Okay, now let's go ahead and plot one using the initial condition of 0. Actually, 0, 3. Let's go ahead and turn that into a 3 and that into a -3. And we'll turn that into a 2 and that into a -4. And I think that will allow us, since basically we're going to be that'll allow us to figure out where 0, 3 actually is, okay? Now, if I want to come down, it's going to be right about, I can't tell for sure, but it's, somewhere in this neighborhood, right? Okay. But of course I'm moving to the right, so it's going to be going up. But that's basically the shape of it, okay? Now, if I know that that's the case, and I know it's going to be greater than 3 and it's going to go up, what we first need to do is we need to find the first tangent line, okay? So here's my step 1. We have a point, 0, 3. We have y prime at 0, 3 is going to be 0 plus 2 or 2. I have point, I have slope, so I have y minus 3 is equal to 2x minus 0, or y is equal to 2x plus 3. That right there is my first tangent line. And now, we'll call that y1. I need to evaluate that at the first step, at 1/2. So I need to go ahead and do y1 at 1/2, and that's going to be 2 times 1/2. That actually makes the arithmetic rather easy. It's going to be 1 plus 3, or 4. So our new ordered pair is 1/2, 4. Now I know that y prime needs to be evaluated also at that particular ordered pair, okay? And of course, if it's going to be x plus 2, that's 1/2 plus 2, or 5/2. Point, slope, okay, y minus y1 is equal to m times x minus x1. And of course, here's where the fractions actually enter in. And I'm going to wind up with 5 halves x minus 5 fourths minus 5 fourths plus 16 fourths is going to be positive 11 fourths. This is y2. And since I'm only going 2 steps, okay, I simply need to evaluate y2 at 1, okay? So if I evaluate y2 at 1, I'm going to get 5 halves times 1 plus 11 fourths, which is going to, of course, be 21 fourths. That is my approximation of what the function value should be based upon a starting point of 0, 3 and a differential equation, a slope defined by x plus 2. Well, that was, let's walk through it again. Okay, so I have slope defined as this. Here's my starting point. Okay, so I got a tangent line based upon the slope at that particular point, okay, which is here, y prime, y prime instead of dy dx. So I had the point given to me, I had the slope from that point, and I get a tangent line. And then I need to reassess. I need to find, once I've taken the first step to 0.5 or 1/2, I get a new ordered pair based upon the input of 1/2, and then I need a new slope based upon that ordered pair. Point, slope, I get a second tangent line, and then of course I would evaluate that at the next step. Now, here's the thing. If I wanted to take a third step, and let's say I was actually trying to evaluate this not at 1 but at 3 halves, I've already basically gotten this. I would do y prime of 1 and 21 fourths, and that would be 1 plus 2 or 3, and then I would just evaluate y of 3, and y of 3 would be, y minus y1 is equal to m times x minus x1, and then I would solve for y, and that would be my y3. Okay, now I wasn't asked for this, but I could keep going if that was actually what was dictated to me in the question stem. 21 fourths. Let's see how close that is to an actual value. Okay, now remember that I was given something that actually is separable. I can actually work this out. I get dy is equal to x plus 2 dx. Integrate both sides. I'm going to get y is equal to 1/2 x squared plus 2x plus c. Now remember, that plus c would be kind of annoying, but I remember that my initial condition of 0, 3 is going to enter in there and actually help me solve for that c value. So 3 is equal to 1/2 0 squared, 2 times 0 plus c. Those both cancel out. So c is equal to 3. So my actual quadratic is that. Okay, well the question then becomes, what is y1? Well, y1 is 1/2 1 squared plus 2 times 1 plus 3, and of course that winds up being 5.5. Well, 5.5 in terms of fourths is what? Well, 5 halves winds up being 11 halves, or 22 fourths. Wasn't my approximation 21 fourths? It's a pretty good approximation, and that's only because I only went 2 steps away, okay? And so what really happened, if you were actually to watch it, if you were to watch it sort of unfold, as it were, you would actually have, this over here, and actually, up like this, and you would have this sort of tangent line right here stopped, and then this sort of tangent line right here, and this point would be very, very close. So what you did is you basically went off in this direction on that first tangent line, stopped at that first delta x, reassessed by getting the new ordered pair and the new slope, okay, and then setting off in a new trajectory to give you that after your second delta x, okay? So that's sort of pictorially what's going on here. And of course, as the, it's going to be a better approximation because it's out here instead of right here towards the vertex. The more you go up on a quadratic, the steeper it gets, and really the more linear it gets, because it gets closer and closer to being straight the steeper and steeper it goes, okay? So if you were to do 2 steps from a point right here, it would actually be a worse approximation than if you do 2 steps on a point further up the quadratic. Okay, let's go ahead and let's do another one. Let's see if we can find a good one. Okay, let's say that we're given dy dx is equal to 1 over x plus 2, and you have y of 0 is equal to 1, and you want to find y of 1, okay, and you want 2 equal steps. So you've been given delta x is equal to 0.5, because from 0 to 1 with 2 equal steps, that's 1/2, right? Well, you know that your ordered pair on step 1 is 0, 1, and you know y prime is going to be y prime. Let's go ahead and y prime, and I'll put the ordered pair of 0, 1. It's going to be 1 over 0 plus 2, or 1/2. Point, slope, okay, y minus y1 is equal to 1/2 x minus x1, and you get y is equal to 1/2 x plus 1. That is my first tangent line. In step 2, I need to go ahead and find what that tangent line value, what the ordered pair is after the first step. So I need to evaluate y1 after the first step, and that's going to be 1/2 plus 1, or that's 1/4 plus 1, or 5/4. Your ordered pair is 1/2, 5/4. Well, y prime at that ordered pair, okay, is going to be 1 over 1/2 plus 1, or 1 over 3/2, or 2/3. Point, slope, okay? So y minus y1 is equal to m times x minus x1. Well, that makes it a little bit sticky because of common denominators and everything like that. So y is equal to 2/3 x minus 1/3 plus 5/4. 1/3 is going to be what in terms of twelfths? It's going to be 4/12. That's going to be 15/12. And so you're going to wind up getting 2/3 x plus 11/12. Now that is y2. And now all you have to do is evaluate y2 after that second step, and you're going to get 2/3 times 1 plus 11/12. That in terms of twelfths is going to be 8/12. 8/12 plus 11/12 is 19/12. That is my approximation. Here's the thing. That actually is a separable differential equation. So we can actually find out what the actual value is. So let's go ahead and do that. I'm going a little bit faster on this one because I've already walked through a couple of examples. If I have dy dx over 1 over x plus 2, remember this is a proportion. As long as the multiplication across is identical, I can actually change the form however I want. So I can actually put dy over 1 and put dx over x plus 2. Okay? That means if I integrate both sides, I'm going to get y is equal to the natural log of x plus 2 plus c. Well, remember that I had 0, 1 as my initial condition. So if I have 1 for y and natural log of 0 plus 2 plus c, then what I have here is I have a c value of 1 minus natural log 2. Okay? And therefore, I have y is equal to the natural log of x plus 2 plus 1 minus natural log 2. Now, here's the thing. I can actually combine that and that by properties of logarithms and get y is equal to the natural log of x plus 2 over 2 plus 1. Now, if I evaluate that at 1, y of 1 is going to be the natural log of 3/2 plus 1. Now, if I can go ahead and get out my calculator, okay, we have the natural log of 1.5 plus 1, and that was approximated as 19/12. That's not that bad, okay? Now, does it make sense that this is higher? It does make sense. Because if the actual function is a natural log function, you know that it's increasing and concave down, okay? So it's increasing and concave down, which means that tangent lines like this are going to be above the curve, and therefore the approximation will be greater than the actual function value. Okay, in the next video, we're going to go ahead and take a stab at a couple of the problems that have been asked in the past on the AP exam using Euler's method. And I think that'll sort of round us out for our purposes. And then, of course, you can email me with any further questions on Euler's method or anything else that your teacher is asking you that I didn't explicitly cover. But I think that'll sort of conceptually at least cover all our bases. So, as always, email me with any questions. Bye.